All right, well, thanks everyone. My name's Rowan McAllister. I'm a research scientist at Waymo. And today I'm going to tell you a little bit about what Waymo is about, together with some of the research that we get up to, specifically in behavior models for interactive autonomous vehicle forecasting and planning. So Waymo, if you're unfamiliar, it's a ride-hailing service. They've got cars that look like this. And you can download and install the app today on your phone. And these are the areas that it operates in. So we've got San Francisco County and Daly City. We've also got areas in Phoenix and LA. And so, fun fact, this area includes the venue that we're currently in. So if at the end of today you want to hail your very own robo-taxi, it can pick you up right outside the doors here. So the operation has been growing. We recently surpassed 100,000 autonomous rides per week. And one of the main mission of Waymo is to be the world's most trusted driver. So it began life as in 2009 as the Google self-driving car project. Ever since then, the focus has been building the world's most experienced driver. So as you might expect, every car gets to benefit from the aggregate of data collected by the entire fleet that is then used to train models that then gets put into each car. So every car gets to benefit from multiple human lifetimes worth of driving. And this is all towards increasing mobility options for people whilst making the road a safer place. And that's no small task. I mean, the great dream of any autonomous vehicle company is to really, kind of look at these horrific statistics and try to work out how can we mitigate this. So, with up to 50 million injuries and over 1 million deaths worldwide on the road by vehicles, the big goal here is, can we do anything to mitigate this, to make roads safer? And starting to drive around over 100,000 trips per week now, we've started to collect a lot of miles, so 22 million miles, which is enabling us to start computing a whole bunch of statistics towards building trust, publicly showing the safety record. And so for more details, you can check out waymo.com/safety. And so what we're looking at here is fewer airbag deployments, fewer injury-causing crashes, and fewer police-reported crashes when we compare against the same amount of miles by human drivers in the same areas. So we've got an apples-to-apples comparison here. And these statistics, by the way, are not collected by us, but really reports from a third-party government body, NHTSA, which we then compile the statistics to show. So as part of building a safe system, one of the solutions, or one of the target areas, is the hardware itself. And so if you've seen these cars around, they've often got a lot of sensors everywhere, and they're really trying to make use of as much of the electromagnetic spectrum as possible. So we obviously see with our eyes, but we can also put LiDAR systems on the car and radar systems. And we put it around the car so it really has a good 360 vision. There's no occlusions. It's effectively got eyes in the back of its head, so it can see really well, especially at night as well. And the other piece of the puzzle is software. And so this is really about kind of decomposing software into how you or I might drive, where we've got, step one, localization. The car needs to be able to figure out where it is. Step two, perception, trying to identify where are the other pedestrians, where are the other cars. Step three, trying to anticipate what everyone might do. Will a leading car in front of me brake? Will someone step out onto the road? And then step four, trying to then decide what should we, the autonomous vehicle, then do. And so here's some examples from some of our first rides, first autonomous rides in San Francisco. So we have some examples here, just kind of going around streets. Sometimes we've got loading vans. You kind of need to, go around. So, there's all sorts of like little complications that pop up. Here we've got a cyclist that's kind of gone through the stop sign. It was our right of way, but in order to be safe, we still need to consider what happens when people do different things, even if it wasn't following the rules of the road. And one of the things that makes autonomous driving hard is that a lot of the data looks like this. It's actually just quite boring for a lot of the time until it's not. And so 99% of the time or more, it's, as you can imagine, you're just like, following the lane. But this is where the software really needs to shine, is in these rare kind of cases where dangerous incidents happen and we need to be able to react fast. So being a fleet, rare instances are no longer rare. They happen all the time. And so we really need to be able to nail down not just how can we be safe 99% of the time, but really all of these edge cases where, which is where the safety matters most. And there's all sorts of examples here. We get a lot of it due to occlusions, where, like you might expect, driving around, you always need to be careful of occlusions because things can pop out at any moment. So this frequently happens. So that's a brief kind of overview about what Waymo is. And I think for the rest of the time, I just wanted to give a very brief flavor of some of the research that we get up to, like what we're interested in and some of the lessons that we've learnt. There's there's paper titles at the bottom of the slide here, and if you can't see it, it will all be on the recording if you want to check out any of these papers later. But I'll go through at a very high level what some of the Waymo research has been about. So behavior modeling in a nutshell is really about at Waymo is really about taking a neural network and then working out how to input what other agents around us have been doing the last maybe 5 seconds, what the state of the traffic lights are, and then what the road network is, like where are the lanes, where is the stop sign markers and so forth. And then one of the common ways that we then do prediction is using Gaussian mixture models in a trajectory space. So for, say, n agents around us, can we predict k different trajectories that we're anticipating they might be considering, and then really looking at what would their xy positions be over t time steps. And so what it might look like from, say, up to from 0 to 8 seconds in the color bar over here is something like this, where we've got agents moving around, and this is what we can use to anticipate their behaviors in order to make safe decisions with respect to what they might do. So that was work that, deep learning really made an impact in Waymo in 2019 with that previous paper. Waveformer is a modernized version of this, which came out last year, which is really about kind of like everyone, how do we make use of transformers given how useful they are? And what the Waveformer paper mainly does is to work out, instead of bespoke, human-curated, specialized encoders for each of these types of inputs, like traffic lights or what other agents are doing or road scenes, can we kind of lean into the bitter lesson a little bit more and try to reduce the amount of specialized knowledge it takes to encode each of these features towards having some kind of scene encoder that we can then use with a Gaussian mixture model of trajectory prediction. So this proved really popular inside Waymo, and you get kind of nice predictions like this, where we've got some multi-modality here, predicting some agents might do a U-turn, some might come around here. Again, not everyone kind of follows the law, and you need to be able to predict that. Jaywalking is a big no-no in the US, and so we need to be able to predict things like this if we're a car approaching a pedestrian that might be weaving between the cars just here. And here's an example of cars waiting for each other for an unprotected left turn. And so one of the other pieces of work was joint future prediction. And this work was really about kind of explicitly trying to understand, do we really actually need to model the interaction between different vehicles? So say we've got kind of 4 vehicles here, A, B, C, and D, and we're looking at the different modes, the different trajectories that they might be taking. One of the things that we might be interested in is how many of these modes co-occur. How many, do they correlate? Do they anti-correlate? We saw that unprotected left turn where one vehicle was really conditioning on the other before it would turn. And so what this work was to do was to say, right, can we do belief propagation to work out marginal probabilities of each of these trajectories together with the pairwise joint trajectories between each agent, then do belief propagation, and then backprop it into this deep neural network that will try to output these directly for something that's very consistent between all of the agents, such that we don't need to do belief propagation at inference time. We only need to do it at offline training, where real-time constraints don't apply. And one of the interesting things here is we could then test, okay, what interaction actually matters? Do we need to model interaction at all? Or do we want to model all of the interaction from the autonomous vehicle to every other car? Or do we actually need to model some of the interactions between different cars themselves as well? And so essentially, like a more correct model of interaction might be, everyone can affect everyone else on the road all the time, which is potentially true at any given point. And part of this work was to expand the common loss metric, so the minimum average displacement error, into a joint space of all of the vehicles. So apologize, you probably can't see it down here, but this loss function is really saying, was one of our guesses close to the true joint trajectory of everyone? If so, we're making good predictions. And one of the things that we found is that actually sometimes the simpler models are better. So this model up here generally told us that the only real interactions we have to worry about at any given time is us with others. Usually the tertiary interactions, you could probably appreciate as a human driver, you very rarely need to consider how person A may affect person B, which would then in turn affect you. It does happen, but it's very rare. So anyway, sometimes the simpler models are better. Another work is leaning into more, some of the developments happening with large language models. So this has obviously taken the AI world by storm, and Waymo's no different here. One of the things that we were interested in is, can we discretize the set of motions into some discrete set of tokens that we wish to predict? So here we might be kind of considering how two cars might sample from a finite set of motions in terms of their interaction with each other. And so this is really expanding that previous paper waveform, which is to take the same backbone, but now to have a causal cross-attention transformer as the decoder. So this is really basically, this is really just an auto-regressive model that's predicting tokens in turn and conditioning on all of the previous tokens to make the next time step prediction. And one of the interesting things about this paper is that it's really amenable to scaling up, kind of like with any other LLMs, like training a categorical model over discrete motion tokens is just very amenable to scaling. And so that's something that we were able to enjoy from implementing like an LLM. And so here what we see is, when we don't have that causal cross-attention, we can predict things like two agents may collide if we're treating them independently, but then when we start to model them properly, we can see that some agents are predicted to wait for other agents before they go. Another big thing inside Waymo, I think, has been distillation. So as you can probably appreciate, so all of the compute happens on these cars, and the car has limited compute inside its boot. And it also needs to be able to make predictions in real time as it's driving down the road. And so one of the things that's kind of of great interest to Waymo is, if we have all of these large models, or even an ensemble of models, can we compress that down into a student model that is able to run on the limited compute in real time, onboard the actual vehicle. And so this is something that we've seen, for some of our metrics, just by, if we were to run things offline and, increase, say, like the number of models that we're dealing with and using ensembles, we do find that we get better loss metrics. And so how can we put this into the vehicle with its limited compute? And so this paper is really about taking that previous model, like MotionLM, taking a set of them, and then basically getting all of their predictions out, clustering them, and then using those clusters to then train a smaller student model. And what we find is that when we compare like loss metrics, or like the soft MAP, or the overlap rate between vehicles, what we find is that we can get for the same level of performance, we can basically do so with less compute if we use this distillation from large models or a set of large models into a smaller model. So that's been really useful. Going back into the tail, the tail of very rare events that can sometimes happen, there's all sorts of things that can happen. So like, we just see all sorts of crazy stuff like, couches on the road, skateboarders hanging onto cars, people dressed up as dinosaurs, the cycling community out in force. There's all of these things we need to be able to deal with. And this is probably the craziest one I've ever seen, is we've got a motorcycle without a motorcyclist on board, just careening down the highway, and thankfully no one was hurt in this situation. It crashes into a hot dog trailer, and so metal goes everywhere. But it's like, it's such a rare event to happen, but it does happen when you have enough vehicles and they're all recording all of this information. And so, how can we deal with stuff like this that just doesn't occur in our data sets so frequently? Other examples of people falling onto the road. I really like this example from Los Angeles as well. So what happens here is the traffic lights have gone out, and so you've got a couple of police officers there that are gesturing for the Waymo to, it's currently stop, but then they soon start motioning for the Waymo to proceed. And you can see the key points up here, the skeleton that the Waymo is inferring. And from that skeleton, decoding the gesture that the police was looking at us and saying, okay, now you can proceed. Anyway, lots of rare events. And so another work, which I thought was really interesting, is work by Yiren Liu called Imitation is Not Enough. This came out at IROS last year. And this was really about saying, imitation learning is super useful with autonomous driving, because people know how to drive already. But what do we do in those tail cases? And so what this work was to say that imitation is actually super useful when you're in a situation that's familiar, where you've got kind of data that in the past, you've seen this situation before, you kind of know what to do. But it's not that effective when you're in the tails, when you're in a situation that's very rarely happened, you don't have a lot of data on what a human expert would have done in such a situation. That's where more explicit reward design from us as human engineers can kind of get in there and say, look, there's a few things we know that explicitly that constitutes good driving, like collision's bad, going off-road is bad, passenger comfort is good, things like this. And so this work was really about how can we combine the best of both worlds. So in this case, we might have some data set or some situations where the car is very much in distribution of what it's seen before, and also out of distribution. And so by training a policy or a planner to both optimize the reward objectives that we care about, that we know to be true. We don't necessarily know everything. A lot of driving is implicit. And so that's why it's still helpful to have this behavior cloning loss. Can we optimize for the log probability of actions that our model of a human expert would take given the state that we're in? It's still good to optimize for this. So can we stay within the realm of maneuvers that we've seen humans do before? And so both of those operated when we're in distribution, but when we're out of distribution, basically we're getting no signal from any demonstration data that we've had so far, but this can still apply. And so what that can mean is, even if it's in a situation that's never been in before, we still know collisions are bad, we still know going off-road is bad. It may not be so comfortable for the passenger, but we can still act safely. And so what we found is this is especially true in the more difficult cases. So on the top percentile of most difficult situations, situations that we see, we find that the combination of the best of both worlds really kicks in then and really helps us out. Okay. A couple more papers so this one is called MOST, and there's been this big debate in the autonomous vehicle community. Different companies take different stances. Should we be dealing with symbols? About what is an agent, what is a traffic light, what is a road? These are all separate things. And can we just do something a little bit more end-to-end? So, we've got LiDAR, we've got vision. Can we just kind of come up with some tokenization or encoding of these things to basically immediately provide the backbone of our scene encoding before we then predict, say, multiple trajectories of where agents may go? And so, having sensors go into a perceptual system that then outputs symbolic outputs, this can be really useful, say, kind of coming up with the road graph, organizing different agents into boxes. It's very low dimensional, it's very interpretable, it's very easy to resimulate. Like, what if this box was somewhere else? What if the road graph had an extra lane or something like this? But where it falls down is where you have certain perceptual failures to novel obstacles. So maybe we never thought to have an aeroplane detector. Something that may happen a little bit more is things like fallen trees or like large branches on the road. There was a very windy day in San Francisco last March, and there was a lot of tree limbs that were all over the road in San Francisco. So it happens even here. But then also certain contextual things that we may not have thought of. So like, what if there's quite a deep puddle? What if the potholes are quite severe? And all sorts of cues that we may not have thought of, like, I mean, we do actually use pedestrian gaze, but like, what if we hadn't have thought of that? So, pedestrian gaze is actually really important when you're driving. If you can see that someone sees you, you know that they're aware of you. They're much less likely now to step out onto the road, and so that's a big cue for safety. And so this work, I'll kind of skip over the details, but it's really, again, trying to get the best of both worlds and saying, it's a false dichotomy to say, are we symbolic or should we just do everything end to end? You can actually do both. And that's what this work was trying to do, trying to use the visual system, but then also the LiDAR geometric, mainly using the LiDAR, working out a geometric representation of everything to put into boxes, that symbolic output, together with features that are coming out of our visual system. And so one of the advantages here is that it kind of helps us out when we're doing, say, things like going off the road graph into a car park that maybe we haven't mapped out now. So now, so in this method, it's able to basically correctly predict that this car from this image is probably going to turn right around here from what it's seeing, even though we don't have the symbolic road graph. Whereas some of the baselines that don't have this visual information, they're kind of out of luck. This is all that they're dealing with over here. And so one of the other benefits here is that when you have these two systems, they can kind of act as, there's more redundancy. So what you can have here is we simulated what happens if we progressively start removing polylines out of our road graph. Does the system just, completely fail or not? And what happens is that, as an example, what we find is if we remove up to 30%, we can remove up to 30% of the road polylines, simulating that perceptual failure, and achieve the same performance as if we had never included any of these end-to-end features. The same is also true for removing certain agents. So, if for some reason we didn't classify, a car as a car, but we're still visually seeing it, here we found that we could still match performance with baseline, removing up to 50% of the agents that we see. And I've got 1 minute left, so I'll briefly go over our last paper, which is scene diffuser. So diffusion has been, super popular in the computer vision community, and it's also of interest to Waymo as well, as a prior of where agents might be in a scene if we want to start with a road graph and simulate where agents might go, but then also how they might roll out through time. So diffusion is really about starting with noise, or starting with an image, adding noise, and then trying to denoise back to an image. And so you can do the same thing with trajectories. And one of the interesting things about this is you can then treat it as all of planning or conditional planning as an in-painting problem. So we can say, what if we know the past and the present and maybe the future intent of our own vehicle, but not anyone else? Can we use diffusion to paint in all of the things that might happen? And just running out of time, I might skip over some of these last slides. But this is really useful for simulation. So we can kind of go back to scenes and say, what if we just perturb what everyone was doing? Would the scene have still played out safely? We can say, what if there was an extra agent in the scene? And we can ask the diffusion system to basically, re-simulate what would have happened. Or we can come up with a completely synthetic scene here. And just very quickly to finish up, one of the big problems with diffusion systems or any other system operating at a high replanning rate is you often get errors compounding. And so in this work, what they actually found is that if we can feed back in our previous plan by having noise for the next few time steps, and then having one denoised step that corresponds to one real time step, and then stepping forward and then popping off, where did we actually end up? What it allows us to do is that if we've come up with a good plan in the previous time step, we can still reuse that plan in the next time step by just adding a little bit of noise and then denoising. And the advantage of reusing previous plans in this way is that we get fast inference time, diffusion, but we also get something that's very consistent and consistent through time. So yeah, I think I'm out of time, so I'll wrap up here. There's some open data sets if anyone's interested, and some challenges. And yeah, thank you very much for coming along.